Okay, in the final part of today's lecture, we'll talk about some optimization issues in policy gradient algorithms. So the first bit we'll talk about is initial state distribution in policy gradients. Just to recall, policy gradients, what they try to do is they try to maximize the policy against the expected return objective, which can also be written as the value function of the policy at the initial state S0 by using gradients. So they would update the policy parameters theta using the gradient of v pi of S0 with respect to theta, which is given by the expected grad log pi times q function of that policy at that state action pair. So this is policy gradients as you have learned it. Now, how do policy gradients depend on the initial state distribution? And why does the initial state distribution even matter here? And that's sort of the question we'll try to answer. So let's consider this simple MDP, which is sort of like a chain MDP. So you start off at state S0. You can go to state S1 by taking action A1, and you can come back to state S0 by the three other actions shown as A2, A3, and A4. You can go ahead from S1 by taking action, go ahead from S1 to S2 by taking action A1, again come back using A2, A3, or A4, and so on until SH plus 1, where if you take A1, you just stay there, and there's no other action that is available. And you get a reward of plus 1 if you end up reaching SH plus 1, and for every time you stay at SH plus 1, you get a reward of plus 1. So it's sort of like a chain MDP, where there are many actions that can take you back to the starting states, and there is only one action. If you follow that through, you will get to the final state SH plus 1, which gets you the reward. So it's sort of like a big. You can think of it also as like or you can think of an analogous MDP, which is the tree MDP, which we saw earlier, where there's only one path that takes you down to the rewarding state in the tree, whereas there are many other paths that can take you back to bad trajectories, for instance, or bad states, for instance. So it's a chain MDP here. And turns out that policy gradient here can be nearly zero at suboptimal solutions. So let's say you initialize your policy with, let's say, some 1/4 probability over all the actions. You'll find that the policy gradient would end up being close to zero, essentially. So you'll not have any signal to improve the policy really. And this can be formalized as a theorem, which I'll not go into, but the theorem, what it really says is that the poor solutions are sort of equally poor because any gradient that you compute would end up being sort of exponentially small in h. And the reason why it is exponentially small in h is because there is exponentially less likelihood that you will reach SH plus 1, unless you know the optimal policy, of course, which would end up taking A1 with probability 1 all the times. So if you start with a suboptimal solution, for all those suboptimal parameters or suboptimal solutions, which are stochastic, for instance, you would probably have that the likelihood of reaching, or the likelihood of obtaining a reward, which is obtained at SH plus 1, is exponentially small in the horizon edge. So it's super small. So you will actually end up needing like a sort of a lot of training time or a lot of samples to even improve upon the suboptimal solution, because all of the suboptimal solutions are sort of equally bad because they're exponentially all worse in the horizon. So that's sort of like the gist of this theorem, and I'll not go into the details of what this theorem does, but it basically says hence policy gradients can be hard to improve. And a lot of this is really related to the initial state distribution, because imagine if your initial state distribution even included SH plus 1. So let's say it was a uniform distribution 1 over H plus 1 or 1 over H plus 2 over all the possible states. In that case, your policy gradient would not be this bad, because you would have seen sort of a high rewarding transition starting from SH plus 1 with high likelihood, because you were also starting from that state. So in that case, you would have been able to learn the policy somewhat better. Now, how can we fix these problems? Now, perhaps there are some ways to fix this problem. For instance, you might want to ignore the gamma to the t in policy gradients, or you might want to not use the discount factor to compute the q function, because that may also make your exponential factor be worse in this scenario. Because for every one transition you take, you're discounting the next, or you're discounting yourself by gamma, a factor of gamma, which is less than 1. So you might want to ignore that gamma to the t factor maybe. You might also want to do some sort of reward shaping, where rewards at later time steps are somehow shaped in a way that make them appear better, so that you can avoid this problem where you see vanishing gradients, which means all suboptimal policies appear equal. You might also want to consider some kind of reweighting of your initial state distribution, and you might want to solve a policy gradient problem under a new, more diverse or more covered initial state distribution, because if you only take the initial state to be S naught, you will probably not find the gradient at all. Whereas if you have HH plus 1 be highly represented in your data distribution for the initial state, you will be able to optimize on that. So this is sort of one of the issues where, again, data distribution matters enough in policy gradients, because initial state distribution or might make your policy gradient be arbitrarily close to flat, may make the gradient be arbitrarily close to a flat gradient in such sort of extreme MDPs where your rewards are hidden somewhere down in the MDP. The final bit which I kind of want to talk about is policy gradient plateaus. So this is an experiment from this paper which I cite on this slide, and what this experiment tries to do is that it tries to train policy gradient with function approximation with on-policy data. So let's say you're given on-policy data, and you can compute true expectations, and you want to do policy gradient, but the bit that is challenging here is that you have function approximation. So you're not just doing tabular updates, you have a function approximator that shares values across states. And let's imagine, for the sake of this discussion, we only had two states in your MDP, and your RL problem was a horizon 1. So it's almost like a bandit problem, except that you still have two states. So you have two states. You can take two actions at each state, and your objective is the policy gradient objective of each of these states added together. So that's J1 for state 1 plus J2, which is the policy gradient or expected reward objective at state 2. And you want to just solve for this problem. So it's a simple one-step RL problem with two initial states or two possible initial states. You want to solve J1 plus J2. And there's no issue, for instance, the issue from the previous slide where the initial state distribution only had S naught in it. We don't have an initial issue. We look at both the states equally, likely in this example. Now, what this paper did was they basically compared. What they basically did was they ran policy gradient on this example in the function approximation setting, which is the which is the first curve, the tabular setting, which is the middle part, and they ran a supervised training, which is the third part. And supervised training is just for a different objective. Now, in all these cases, what they plotted here was in the top row they plotted how J1 and J2 change as a function of the learning trajectory. So they're basically plotting the learning curve as a wavy line through the space, and they're basically looking at what the value of J1, what value of J1 and what value of J2 correspond to each other at that point of the learning curve. And they're also plotting in the plot below. They're plotting a typical learning curve where steps represents the number of gradient steps you have made, and the y-axis represents the value of J, which is the sum of J1 plus J2, the total expected reward objective. Now, it turns out if you do this, you would find that a lot of these learning curves would end up plateauing a lot. So they would end up plateauing a lot, and then they would rise up to the optimal solution. So here, for instance, they would plateau at 1, and then they would eventually rise up at 2, and some of them may not even rise. So why is this sort of plateauing behavior very prevalent? And you probably also have seen these in your homework assignments, where you find that policy gradients sort of plateau a lot, and then they increase back and plateau a lot again, and so on. So it turns out that when you optimize these two objectives, which means you're optimizing the expected reward at one state plus the expected reward at the other state, you might end up sort of overfitting on optimizing one of these objectives more than the other objective. And the reason why you are doing that is because if you hit a saddle point of this optimization problem, which ends up being the solution where you optimize one of the objectives well and not the other objective, in that case, you might just want to stay there. You might just want to stay close to that corner because that's a good solution for your optimization problem. And once that happens, you'll find that your curve plateaus until there is enough perturbation or enough noise in your gradient descent procedure or in your optimization procedure that can take you farther away from there and take you again to the next final optimal solution that optimizes both of them. So it's almost like you have these two corners, which is 1, 0 and 0, 1, that are saddle points, and you can hit them and be there, be happy there. But you want to actually reach 1, 1, which is the other point here. So if you want to go there, you kind of need some perturbation that pushes you towards 1, 1. And that happens only less. And when that happens, for example, on the blue curves here, you actually rise very quickly directly to the optimal value of J, as shown in the figure. And even tabular RL suffers from this issue to some extent. And to some extent, this issue is just coming from the fact that the policy gradient objective is non-convex and so on. But if you look at what happens with function approximation exacerbates this issue. So there's larger plateaus with function approximation than with a tabular setting. And supervised learning has almost no such issues. It's just all rises very quickly. And because of this, all of these issues, initialization, etc., become very important now. For instance, if you initialize your policy at a location where J1 and J2 correspond to one of those locations in the middle part of the square on the top row. So you initialize to a policy that is kind of like very good in that J1 and J2 correspond to the middle part of the square. In that case, if you look at how those trajectories evolve, you would end up actually going to the optimum directly. So you'll not suffer from these plateaus. You'll directly follow one of the blue paths in the leftmost figure and get to the optimum. So initialization, etc., become very important now because policy gradient suffers from this weird issue where it can converge to a saddle point first, stay there for a long time, and only then improve back to the optimal solution. And as we show on the next slide, this is also affected by attraction to suboptimal solutions just because of this issue to some extent. And partly one more point that is not sort of covered here, which is that the reward values play a lot more role in this sort of weird plateauing behavior of policy gradients. So consider a three-armed problem now. So far we were looking at two actions and two states. Now consider it was just one step, it's just a banded problem, but you have three arms. So you have three actions possible and one of those actions is optimal. And the arm one is the optimal arm here. Turns out that if you initialize your policy to be a good policy, so you're basically learning a policy that learns to predict the optimal arm. So it should be basically predicting arm 1 always, but you initialize your policy to be, let's say, 0.3, 0.3, 0.4 or something like that. Now, it turns out that if you have a good initialization, you'll find that your learning curve just rises up very quickly, as you see with pi theta transpose r, which is the expected reward. Whereas if you have a bad initialization, you'll again see this behavior where you saturate at a suboptimal plateau and only then rise up eventually. Turns out that in this visualization from this paper from ICML this year, what they showed was that if you have a wrong initialization, if you have a bad initialization, you might end up converging to a poor solution first, which is sort of very similar to the saddle point from before, and you might only then escape that point eventually and get to the optimal solution. So your convergence rate might be super slow. You might get stuck in this plateau for a long time. Only then you might be able to optimize against that plateau. And your learning curve would exhibit this plateauing, this gradual plateau style behavior. Whereas if you have a good initialization, you may not suffer from this issue, as we show on the first plot. Now, the bit that is the most interesting here, perhaps, is that this which solution is a good initialization versus which initialization is a good initialization versus which initialization is a bad initialization depends on the difference between the reward values. Because the policy gradient objective literally just depends on the rewards, because it's the expected return under the policy pi, right? It's pi dot r in a sense. And so the reward values contribute to a lot of these issues just because you have this arbitrary scalar multiplied to them in the objective. And so initialization matters, reward values matter, and a lot of this also matters in the offline setting when you do, let's say, important sample based policy gradients, which we talked about briefly in the offline RL lecture, but we'll not go into that in this part of the lecture today. Okay, so to summarize, we sort of covered three broad things today. The first bit was about how overfitting, which is due to sort of observing fewer samples, is not just about how sampling error affects standard supervised learning, but we also looked at how Q-learning updates may suffer from this rank collapse problem because of finite samples, because you're of limited data, just because of the update and the regularization effect of gradient descent type optimization schemes. We then also looked at how data distributions matter a lot for RL problems for both Q-learning and policy gradient algorithms. For instance, for policy gradient algorithms, if your initial state distribution is super narrow, you might end up not convert. You might just suffer from a plateau. And similarly for Q-learning algorithms, if your data distribution is such that it may not be able to correct errors in the corresponding target values, which should be used for the backup, you will not be able to optimize your Q function to achieve to obtain Q star, and that will be bad. We also looked at how how these policy gradient objectives and the fact that your objective consists of this reward function multiplied to it, and you're iteratively training on that objective, along with issues pertaining to function approximation may affect solutions and convergence in policy gradient and Q-learning methods, in terms of plateaus in policy gradients, in Q-learning in terms of error correction, and in terms of just sort of like poor performance, as we saw in the distributions part of it. And there are several many open questions that we also kind of went through in this lecture, as well as many other questions. And a lot of this area is sort of very new, not super understood yet, being actively researched upon. So there are sort of very exciting questions to be answered still in this part. Yeah, thank you.